Hello, this is our project SuperMic, an open source 8-microphone beamforming solution with the Skywater 130 PDK. My name's Armaan, and my teammates are Morgan, Ria, Asmi, Vic, and Sanjay.
First off, what is beamforming? Beamforming is a technique used to improve the signal-to-noise ratio of a microphone array. If you have a source signal that you want to focus on, but is being drowned out by a noise signal in a different place, you can use an array of microphones, like in the image, to collect the signals out of phase, use time delays to put them into phase, and then average the signals to implement delay-sum beamforming, one of the most common beamforming techniques that we're using in this project. And on the left, you can see some common beamforming applications.
Now let's talk about our problem statement. As of now, beamforming equipment is bulky, expensive, and also hard to get by. So the question we wanted to solve was how can we create a low power and low cost solution to implement directional high signal to noise ratio, or SNR, microphone beamforming.
This is a high-level schematic of SuperMic. First, 8 microphones go into a DDR to SDR converter. Then they pass through a set of CIC filters to improve SNR and demodulate the signal. Then they pass through delays and an adder, that's delay and sum beamforming. Then they get routed to an I2S bus. Additionally, we have implemented microphone pass-through after the CIC filter, so that if you wanted to do something such as adaptive beamforming, it is still very easy and accessible.
So the microphones we're using are MEMS microphones. So MEMS microphones convert analog sounds to digital. They do this using PDM, or pulse density modulation, where a higher amplitude of sound means a higher density of ones, and lower amplitude means higher density of zeros. Also, left and right microphone signals interview to achieve dual data rate transfer.
Now, more on that. Microphone signals are in something called double data rate, where you have 2 signals per clock cycle, one on the rising edge and one on the falling edge. In this way, the signals from 2 microphones are combined on 1 wire. However, to do any sort of processing, we need to split this out back into 2 wires, convert them back into SDR mode, single data rate. We do this through the logic shown over here. And that solves the problem. We split it into 8 different wires, each with 1 microphone signal.
The SuperMic uses a CIC filter, a cascading integrator comb. It's essentially 3 integrators followed by 3 differentiators. The combs you see on the screen are the differentiators. So this removes the noise, also reduces frequency to 48 kHz.
In this example, a very noisy 3 kHz sine wave signal is getting passed through the CIC filter, and the output noisiness is greatly reduced.
After the filters, the signals are fed through linear buffer delays, which introduce a longer path for the data to traverse. These are implemented using shift registers. We have 32 predefined delay configurations for customizability.
Next, we have the 22-bit adder. So the 22-bit adder is used to handle the summation of 8 19-bit binary numbers. So this adder consists of full adders to handle the bit-by-bit addition. Also, we utilized a sign extension so that we could extend the smaller 19-bit inputs into 22 bits.
Then SuperMic needs an I2S bus to transmit the audio data in a serial format. We begin by loading 32-bit audio data in parallel into shift registers. From there, we serialize it using multiplexers, or muxes, which shift out each bit in sync with our clock signal.
Now this is how we verified SuperMic worked. We first generated a clock signal through this Raspberry Pi and fed it into this BASICs 3 FPGA, which was graciously provided by BWSI. The signal is then routed to a series of microphones, and then the output is sent to a logic analyzer so that we can visualize the output on the PC. This is the output from the logic analyzer. We had 2 microphones, one that was close and one that was far away. And we noticed many characteristics that showed the time delay of arrival, a crucial characteristic for beamforming.
Now, here's our chip rendered in OpenLane. Initially, we were using a whopping 24 tiny tape-out tiles with about 195,000 gates, which is massive. But as we optimized our design by switching from 16 mics to 8 and increasing the chip density, we were able to reduce the number of tiles to just 16, 12,000 gates, saving tons of space.
This is a demo of audio before and after it has been run through SuperMic. Before.
Clarets are valued for their flavor and for their tonic properties.
It's very noisy. This is audio after.
Meanwhile, all the rest of the people in the castle have been awakened.
It's far easier to understand, and there's much less noise.
SuperMic enables cheaper, smaller, and higher efficiency beamforming. It has applications in hearing aid quality, teleconferencing audio quality improvements, sonar improvements, fetal heart rate tracking, and ultrasound improvements, with different mic types enabling different applications.
So if you have any questions, you can ask us right now, or look at our website or GitHub, both linked over here. Now, they say that a journey of 100 miles begins with one single step. Now, our journey to 1 trillion gates has started with BWSI. So we thank you to our instructor, the TAs, the admins of BWSI, and our fellow classmates.